It was the French physicist Louis de Broglie who proposed a radical new idea, that electrons actually behaved like a wave. This proposal, as strange as it seemed, resolved all the problems with the Bohr atom. The electron was behaving like a spherical standing wave, with the discrete energy levels due to the different oscillating modes permitted by this system. Just like a guitar string can only vibrate at certain modes. Another bizarre thing was that when Schrödinger worked out the mathematical form which these waves must take, it turned out that they were not physical, since, as mentioned before, it was in mathematical terms an imaginary or complex-valued object. The fact that electrons can behave like waves was also shown using a similar double-slit experiment as Young had used to prove light was a wave. Only now, instead of light, a beam of electrons hit a screen containing two slits, and a second screen which registered the distribution of electrons which passed through these slits. In the case that the electrons would behave like normal particles, then two clear bands should appear on the second screen, which correspond to the two slits in the first screen. If the electrons would behave like waves, then one will see a series of high and low intensity bands appear across the whole width of the second screen. These series of bands are due to the waves interfering with each other and themselves, or diffracting. Interestingly, this is true even if just a single solitary electron were to be shot at the double slit. So in reality, the electron behaving as a wave traverses both slits at the same time. It exists in two locations at once. This ability to exist in two locations at once is also known as the quantum mechanical property of superposition. As we will learn later, superposition can exist for many other physical properties outside of just position. The debate over what this quantum mechanical wave function represented physically was somewhat resolved by 1927 with the so-called Copenhagen interpretation. At the heart of this view is Max Born's thesis that the wave function is simply a mathematical object which can yield a probability density function. Thus, it has no physical meaning outside of the statistics and its ability to predict a particle's behavior. Needless to say, physicists hated this interpretation, though it has become increasingly accepted in the ensuing 80 years. Initially, many clung to the belief that the wave function was masking some other local physics that we just couldn't measure. These were known as the hidden variable theories. To support this thesis, physicists Albert Einstein, Boris Podolsky, and Nathan Rosen, and others came up with a thought experiment, now known as the famous EPR paradox, to expose what was considered an absurd consequence of quantum mechanics. The fact that two particles, after interacting and becoming entangled quantum mechanically, could affect the state of each other after being separated by great distance. However, this phenomenon, which Einstein derisively called spooky action at a distance, was subsequently demonstrated through many experiments, and the notion of quantum entanglement is now not only accepted, but used to develop new technologies. In 1964, John Bell put forward his famous theorem which states, "No physical theory of local hidden variables can ever reproduce all of the predictions of quantum mechanics." He further proposed an approach to test the validity of this theorem by measuring the occurrences of correlations between measured states of particles which were quantum mechanically entangled. Experiments testing Bell's inequality in 1972, 1981, and more recently 2015, have so far laid to rest any theory of local hidden variables. It was actually Heisenberg himself who grasped the connection between quantum mechanics and the Platonic viewpoint regarding the essence of reality. I think that modern physics has definitely decided in favor of Plato. In fact, the smallest units of matter are not physical objects in the ordinary sense. They are forms, ideas, which can be expressed unambiguously only in mathematical language. There are several important aspects of quantum mechanics that lend themselves to the Platonic interpretation. The first is a clear separation between the object measured and the mathematical form which gives rise to the object. To use the cave allegory, the shadow and the object casting it. Then there is, as Heisenberg acknowledged, the fact that the units of matter are not physical objects in the ordinary sense. There is also additional subtle evidence for the correctness of Plato's views, which flows from the fact that the fundamental physical interactions are governed by probability and not pure determinism. If we accept the assumption that the universe is either spatially infinite or eternal, assuming a finite difference scale, the logical consequence is that all forms are eternal, because probabilistic physics operating over any kind of infinity will most surely yield all outcomes that have a non-zero probability of occurring, even if that probability is infinitesimally small. This means in a universe with infinite space, all these forms must exist with an infinite number of occurrences. And even if the universe is eternal, all these forms would occur an infinite number of times. In fact, the only escape from an infinite multiplicity of identities is offered by the idea of a unique human soul. Either way, death and decay would seem to be an illusion, a simple product of our limited sampling. It's safe to say that we are currently in the midst of a mini-renaissance in our understanding of questions related to the fundamental nature of quantum mechanics. I believe this has in part been fueled by the recent drive to develop quantum computing, which at some level has forced applied and theoretical physicists to try and resolve these outstanding issues. Additionally, in recent years, there have been some profoundly interesting and exciting theoretical developments in string theory and the decades-long quest to understand how gravity might arise within the framework of quantum field theory. These ideas suggest that the very construction of space-time is a product of quantum entanglement or quantum correlations. Here, the quantum entanglement structure, which builds up space-time, retains quantum information about the whole system on the boundaries. Thus, the very construction of space-time in this model represents a type of error-correcting code. The upshot of all these new understandings is that fundamentally, relational information may not only underlie matter, but also the very structure of space and time which we inhabit.